We can use the IPv6 addresses, and in this case we will provide the list of IPv6 addresses. So the node in the middle, they keep on processing the IPv6 addresses and the traffic finally reaches to the destination. So just to go through what is an IPv6 address, how it look like, what are the different fields. So I will quickly go through it. So in case of IPv4, we have, this is an IPv4 header. We have version, the type of service, total length, and time to live and protocol, source destination. So if we compare our IPv4 header with the IPv6 header, we will see what are the different fields that have been kept in IPv4 and what are the new fields. So here, based on the color, you can identify from IPv4 header, we have taken 3 fields. They are kept with the same name. One is the version. So it is also in IPv4 and the name is same. Another is the source address, and the third one is the destination address. So these 3 fields actually, they are also in IPv4 and present in IPv6 as well. There are 4 other fields which actually are copied, or they have been taken from IPv4, but they have been renamed just to have a more like more logical name, or the name which is more relevant to their functionality. So one is type of service, another is it has been renamed from type of service to the traffic class. So the another field is the total length, which has been renamed as a payload length. The third one which has been renamed, it is the time to live, and now it is called hop limit. The next one is the protocol, and it has been named as a next header. So actually our focus will be on this next header field. The other fields which are like color red, so these are not copied to the IPv6 header. When I am saying copied, that means when they were deciding the IPv6 header at the ITF, they actually thought these are the redundant fields, or maybe when IPv4 was started, they have some sort of purpose, but it doesn't make sense to have same fields in IPv6 as well, in IPv6 header. So that's why these fields are no more present in case of IPv6 header, but you will find them in IPv4 header only. So there is one new field which has been not present in IPv4, but it is in the IPv6 header, which is the flow label. There is some overlapping here, so just to avoid this, I am moving on. So you can see this is the IPv6 header, and if we just have a look with IPv4 or compare it, it look more simpler, because one is the less number of fields, another could be like there is like not any field present which is not in use. But in case of IPv4, we were having few fields which were there in every use case. They were maybe not even used, and few of them, they were considered to be a burden, like they have to be there and even they are not used. So as I said earlier, this is the like description for the field. So version is like in the version you will find v4 or v6. That means if the number is 6, the we can identify this is IPv6 header. The traffic class, this is used for the like for traffic in, for the QS, sorry. And flow label is actually used to identify the packets which are between same source and destination, and they are part of one flow. So then the device in the middle, they can treat them accordingly to provide them this like same kind of service. Just to give you an example, like we are part of like one workshop here. So that's mean if we are going from this room to for the lunch or for the tea break, so the based on our identification, the guest, the host, it can give us similar treatment. So similar devices can identify the packets who belong to same flow, like they are part of the same data stream. So they are given the same treatment based on this flow label. Then we have the payload length. This is give us the total payload length we have in this case. So the value will be extension header plus the data. So basic header, it is not included in the payload length, whereas in IPv4 the basic header, it was included in the total length. The next one is the next header field. So this is our most important field for the upcoming segment routing discussion. So in this field actually it identifies the type of information that's going to come after the basic header. So whatever the upper layer header is going to come after the IPv6 basic header, it is mentioned in the next header field. It is similar to like you are giving someone some information, and along that you are also going in what is the next information he is going to receive or he should expect from you. So once a router or a device receive the IPv6 basic header, by looking at the next header field, it would be able to identify what is the additional header which is going to come after this. So remember, this next header, this will be additional header here, and then hop limit is similar to TTL. So this will keep on changing when the packet is moving on, just to reduce it by 1. So if packet does not reach to destination until the limit has reached, so it could be dropped and it does not remain within the network forever. Source and destination is like source address from where the packet is being sent, and destination is your destination address. So if we take a like where the next header fits in, so this is your basic IPv6 header, like what we discussed in previous slide. So this is your basic IPv6 header, and here within the next header field we specify upcoming or the upper layer header, and in this case we have the basic header, and the after that we have TCP header. That means we are carrying the TCP data. So then we are going to mention the number for the TCP, which you can see here is 6. So we have to specify 6 against the next header field in the basic header, so the device can know what is the upper layer data. After that we will have the actual payload, because TCP is again, it has its own header, and then there will be the upper layer data which will be the actual header. The next example is for the fragmentation. So in case of IPv6, one of the biggest difference with the related to IPv4 is the fragmentation. So the as per the IPv6 like RFC or this standard we have, the mandate is the devices in the middle will not fragment or will not take part in the fragmentation. It is the responsibility of the sender to fragment the packet and then send towards the destination. If he is sending the packet which cannot reach to the destination because of the higher MTU, and the packet is getting dropped, then a message is sent back to the source along with the information. This information is about the MTU, like what is the maximum MTU it should use, and then it will actually again prepare the layer 3 packet for the IPv6 according to the new MTU size, and sends this packet, it will try to send it again. So that's why within the basic header, if we are doing fragmentation, then we will specify 44. It will indicate like we are doing the fragmentation, and the upper layer is like the fragment header, and after that we can have the TCP header and the actual data. So this you can see, this will make a chain like, and we have to specify all the next header whatever coming after that. So this is your basic header. This next header is called the extension header, and then you have the upper layer data. According to our need or whatever the next header we are going to use, we have to specify accordingly. Like if we are sending the ICMP packet, then we have to specify 58. If we are using like encryption, then we have to select like 50 to encrypt it, and for authentication we have to use 51. That's why it is said like in case of IPv6, the IPsec support is there by default. That doesn't mean like when you are using IPv6 it will automatically create the IPsec or not, but within the header it has the support. So by just including the number, you can attach the IPsec, and then it could be established as well. So this is again the showing us the basic IPv6 header. Then if we have specified the next header field equal to 0, so it is the hop by hop option header. Actually within the IPv6 there is another mandate. The devices in the middle, they are not going to process the upper layer header other than the basic IPv6 header until unless hop by hop option header has been mentioned. All other headers, they are going to be processed by the destination, not by the devices in the middle. Until unless they find their IP address in the destination field, then they are going to address and check what is the next header field. So this is our basic IPv6 header. This is our IPv6 payload, and it includes the extension header plus the upper layer data. So this is the complete IPv6 packet we have. So I will switch back to segment routing. So as we have seen earlier, in case of like SDN architecture, the data plane could be segment routing, and within segment routing we have two options: either use SR-MPLS or we can use SR-V6 to forward our data, because data plane is about the forwarding. That means we can use either segment routing MPLS, or there is another way. So our objective is to deliver the VPN traffic using the IPv6 data plane. So we can see we have two Cs here, C1 and C2, and within that we have the IPv6 domain. So the C1, it will send the traffic, and we want to pass on the traffic to C2 over this zigzag path. So we have to include the node segments for the devices in the middle from where we want to traverse the traffic. So rest of the things are similar, like traffic will come in, and the C will just send the plain IPv6 traffic, which would be L2, L3 or IPv4. The P1 is the one which is going to build the segment routing header. So once we build the segment routing header, first we need to give the list of serviced or the nodes which we are going to traverse. In this case we have identified R4, R2, R6 and P2. So the first one will be R2, R4, R2, R6, P2, and the segment left field it will be n-1. So n is 4, -1 is 3, and destination address will be the first node, which is R4. So after this the packet has been constructed. The destination, based on destination address, P1 will process the packet. So it will check the destination, it is R4, it will do the IP lookup. So P1 will do the IP lookup for R4 and send the packet over the direct link to R4, because it is directly connected. This is the shortest path. So after that, as we know, this is our source node. So the packet will reach to R4. So R4 will match the destination address, it is same as its local address. So then it will actually do the segment left field, it will minus the segment left field by 1. So now the segment left field will be instead of 3 it will be 2. So it will go to the position next. So remember we have 0 here, it's not like 1, 2, 3, it starts from 0, 0, 1 and 2. At 2 is R2. So it will put R2 address in the destination address and then do the IP lookup. The fib lookup is like the IP lookup, and then it will forward the packet towards R2. So R4 in our case it will be the segment endpoint node. So R2 will receive it, then it will do the same thing or the same action which R4 has done. Local address is same as the destination address. So it will decrement the segment left field by 1. So now segment left field will be reduced by 1. It will be, instead of 2, it will become 1. So at 1 position the pointer is pointing to R6. This is 0, this is 1. So it will move the R6 address in the destination address and then do the fib lookup, and based on the shortest path it will send the packet towards R6, and R2 is our segment endpoint node. So the packet will reach to R6, and then R6 will see what it will do. It will decrement the segment left field by 1. So the segment left field will be equal to 0. So it will go to the position 0, and it will take the PE2 address and put it in the destination header, and then do the fib lookup and forward the packet. So this is, again, this will be our R6 will be our segment endpoint node. So once the packet reach to the PE2 router, so the destination address is same as the local address, and the segment left field is 0. That means there is no more segment left to process. It will scrap the SRH, and it will look whatever the header coming after the segment routing header, and it will process that. So based on that, it will look up the packet it has in the payload, and it will forward it to PE2. So another thing we need to note, like in this case, the segment, the next header value corresponding to the type of VPN service. So within the header after the SRH, when we have the SRH, after that we have mentioned what is our corresponding VPN service. So this will be also be identified by PE2, and based on that it will take the appropriate action and send the packet towards CE2. I just want to show you one table, and then I can wrap up. So you can see this table. Don't be scared by looking at it. So these are the name of the segment routing endpoint behaviors that it has. That means we can provision different kind of VPN. So how the device is going to identify like what kind of VPN service it is going to deliver. So we have to configure on the device which kind of VPN this is. So once the packet reaches to the device, the VPN we have configured, it can identify based on the segment endpoint behavior, and then take the appropriate action. Just to give you an example, like if the packet is received with the end.t function, that means the endpoint with a specific IPv6 table lookup. So it needs to look up in a specific IPv6 table instead of the default IPv6 table, and then find the destination and forward the packet. But if it is the case of like IPv4 or IPv6 VPN, we can say here end.dt4. That means once you receive the packet, your endpoint, you will receive the packet, D encapsulate, like D is D encapsulate, T is for the table, and 4 is for the IPv4. That means D encapsulate the packet, look into the specific IPv4 table, and then forward the packet. And you can find here the application IPv4 L3 VPN and IPv6 L3 VPN. So if you want to support the VPN service, you have to implement this function. And this is not a very complex. You just mention this n.d.tx against the VRF, and then that VRF becomes the corresponding is attached to the corresponding endpoint behavior. Okay, so due to the time, I can only go up till this point. So now we will move on to the next part, which is you have to fill the survey. So what I can do is I can let me shorten the URL for the survey, and then it will be easy for you. So although if we see the survey link is this one, so either you can type it, or I can put as a QR code so you can scan it. So if you want to type it, this is the survey link. So you can like give us feedback regarding the delivery of this workshop. I will put this as a QR code as well. So either you can type this URL or you can scan the QR code. It will take just like couple of minutes to give the feedback. There is not too many questions. Mostly you have to just click, and there are very few, 1 or 2 questions where you are need to type if you want to type. When we have like 300 plus slides, so I will also upload those slides as well. Other than that, you can see here the SRv6 lab is also there. So you can do this lab later on when you have time. So the labs are available 24/7. Whenever you have time, you can do it at any time. Going forward, like where you can find more stuff later on regarding the segment routing. So I have put these 3 links here, so you can check them as well. One is like on the YouTube, there is a complete course based on the segment routing material available on the segmentrouting.net website, and you can see here there are around 37 videos. So you can also check if you are more interested to know about maybe some of them. You will be refreshing these things. Few of the topics which we were not able to cover due to the time, they are also present here, and the configuration lab is also there. So this is based on the Cisco. Just keep in mind, I'm not promoting Cisco, but someone who has posted this video, he has used Cisco material. And the same slides, they are available on segmentrouting.net website as well. So you can check from there. So these are the additional resources which maybe help you if you are like follow. There are other like links, and so I would leave it to you. When you have time, you can explore more. These are called the SR domain edge router, like they are on the edge of the network. So the router IDs are the segment IDs. They are actually the advertised using the IGP. That's mean we use the OSPF or ISIs to advertise or advertise the segment the segment identifier or the seeds to each other router within the segment routing domain. So they will have the reachability through the IGP. That's mean we can use the shortest path routing in this case as well. So the other nodes, these are also the segment routing domain, SR domain router we can say. And in terms of security, we need to secure our segment routing domain. Like earlier we discussed, we need to secure these domains, like the packet, any segment routing header packet should not enter from the outside the domain. And we need to just drop it. If the destination is our network, our source is our network. Because if customer is sending packet, it is attaching the segment routing header, the destination should be beyond your network. So the same saying, if destination or source address is from the block we have reserved for our segment routing domain, we need to drop the packet. If from our network, from within our network, if we have a destination which is part of this and the source address is not from this network, then we also need to drop it, because that means from within our domain we are doing something wrong. So not only from the outsider, we also need to think from within our network what should be the better way to generate the traffic, and we should not generate any traffic which actually doesn't make sense. In that case, the destination address is our own address, but the source address is not from our segment routing domain, which is this /48. So we need the protection for overall domain and protection on each node as well. So how the segment routing happens? According to the segment, we have one use case, like how we can route the packet from a host to host using the segment routing traffic engineering, and what will be the packet flow. So if our objective is to deliver traffic between host 1 and host 2 via router 5, so what would be the list of segment? So this is our objective. So in this case, since H1 and H2 both support the segment routing, so H1 can build the segment routing header packet. So it will put its own address as a source address and the destination address as the R5 address, because we want the traffic to pass through R5. And the ultimate destination is H2 in this case. So segment left is equal to n minus 1. So n is 2, minus 1 is equal to 1. So H1 will make this segment routing header packet, and then after that it will look at the destination address. So H1 will look at the destination address. It is R5. So it will send the packet to the next stop, which is R1 for R5. So once it reaches to R1, since the local address it is not same, so this is how the packet will be when it reaches to R1. So the destination address is R5. So it will just do a lookup because R1 is not same as the local address as the R1 has, and it will send the packet towards the R5 router. So once the packet reaches to R5, it will check the destination address is same as the its own address. So it will decrement the segment left field and copy the next address in the segment list to the destination address, and then do the lookup based on the destination address and forward it to the next stop. So the traffic will reach from R5 to R2. So once it reaches to R2, it will check the destination address is H2, which is not same as its own IP address. So it will do the lookup and send the packet towards H2. So once H2 receives the packet, the destination address is same as H2. So and segment left is 0. That means there is no segment left. So it will in that case it will remove the SRH and check what is the payload, and it's the destination, ultimate destination. The second is host to host communication using the shortest path first. So in that case, what will happen? Do we need SRH in that case? Because there is no traffic engineering requirement, so that means we do not need to put the SRH. We can just put the source and destination address. So it will build the IPv6 packet without the segment routing header, because we do not need to attach it. So it will be just a IPv6 packet without any extension header and with the payload. There could be extension header like for TCP or UDP, not for the segment routing header. So in that case, traffic will reach to R1. R1 will look at the destination address. It will send towards R2 because this is the lowest metric path. It will reach to R2, it will send to R3, and finally reach to H2. So once it reaches to H2, destination address same as local address, it will just look at into the payload and process the upper layer, whatever is like TCP or UDP, if it's mentioned within after the next header field. So what we have observed in case of segment routing header, when an SRH is not used, so in that case the shortest path routing is actually used, and the data plane routing behavior, it is like similar to standard IPv6 routing. It's not different than how we do an IP lookup or how we treat, even in case of IPv4 it's similar to that. And the another thing we need to be like aware of, that the destination address of outer IPv6 header, it's actually explicitly mentioned as an SRv6 SID, but it is routed through the IPv6 network as an IPv6 packet. Although it is like the source and destination, they are supporting the segment routing, but the treatment how it is happening, it's just a normal IPv6 packet is routing, and the devices in middle keep on forwarding. Again, our addressing plan, we have locator, function, and the arguments. So how we will be able to deliver the VPN traffic? What is first is the use case using the traffic engineering. So in that case, our objective is to deliver traffic from CE1 to CE2, and traffic should go from the R4 to R2, via R4 to R2 and R6. So this is our path. We want to go from P1 to R4, then go to R2, and then again to R6, and then back to P2. So what will be our C1 will send the like C1 can send IPv4 packet, it can send an IPv6 packet or a layer 2 packet as well. So it does not has to be an IPv6 packet, because this is SR v6 domain, so that means it can carry any traffic, either IPv4, L2, L3, whatever it will be, it will just carry it. So C1, it's going to send either one of these kind of packet. So P2 has to send the packet to P1 has to send packet towards P2 within the context of the VPN, mean whatever the context IPv4, IPv6 or L2 is. And just think about, like, we are sending the VPN traffic, that means device in the middle, they are going to be transparent with respect to the VPN. Okay, so this C1 will send the data packet, P1 will receive it, and then P1 will build a segment routing header with source address, its own address, destination address. Before putting the destination address, it actually needs to build this segment list. So based on our objective, we want to go to R4, so it will put R4, then R2, so R4, R2, then it will put R6, and then it will put P2. So we need to set the first node in the destination address, so we will put R2 in the destination address. And then P1 is going to do an IP lookup, and the segment left field we also need to set, which is equal to n-1. So we have 4 nodes, so it will be n-1 is equal to 3. After that, it will send packet towards R4. Anyone want to process this packet? Who is going to volunteer? Okay, so we can go for break.